How do I? No, capture. Okay, let's do this. Oh, why am I in Diop, man? No, we don't want Diop. I'm bold, I'm eager, she loving my demeanor. Oh, hello, bitches. Hello, bitches. Just bitches. Alright, bitches. Telling on the business. Sit in their own core and own gun. You see the conversation? Yeah, right. So, I don't have the patience to do a hash map. Fuck. Let me just do it. We're using a stack for this one. I don't want to do it. Fuck no. Rather do something else. Should I go trees or binary search? Yeah, binary search had some overlap, unusual overlap, I should say, with stack. And it's my duty to, what is binary search? Let's do this. So what is you're given a sorted array of distinct integers and a target value. Return the index if the target is found. If not, return the index where it would be if we're inserted in order. You must write an algorithm. And okay, I need to find. Oh wait, it's binary search. Okay, and return the index where we found it. Okay, I need to find the index. If it was I need to write it in log of n to find the time complexity of it. So how would you do it in binary search? I think we should use a two-pointer. And how do we actually do it? I think using a two-pointer is the right approach. I mean, two-pointer in each side. I need a... I need down. I need to take a piss. Okay, let's... what the fuck is this? Fibonacci series. I ain't doing that, bro. I ain't doing that, lil bro. I ain't doing that, lil bro. I ain't doing that, lil bro. You know what I'm saying? Ah, my nose hurts. Right, okay, I need to do like 80 of them to get like decently good. Why is it this only, bro? I need to do like at least 80 to get good. So let's just like jump into it. Solution of this. I don't like the solution being fed that way, honestly. I'd rather like go here. Who has like the shortest, you know what I mean? This is the shortest one, of course. I'm going to save time.
Hey guys, Greg here. Let's solve search insert position leak code number 35. So we are given a sorted array of distinct integers, and we're also given a target value. We need to return the index if the target is found, but if it's not, we should return the index where it would be if it were inserted in order. And they give you a massive hint that you should do binary search here by saying you must write an algorithm with big O of log n runtime. Okay, so let's look at an example here. 1356, target of 5. We can see that we do find it, and so we just return the index, which is 0, 1, 2. Now for this example, we have the same array, but we're searching for 2. Now we can't find 2, and so where it should be is right here. We can see it should be in the second spot or the 1 index, so that's what we return. And in this last example here, we have a target of 7, or where that's the number of the array, or where that's calendar array, but we're searching for 2. Now we can't find 2, and so where it should be is right here. We can see it should be in the second spot or the 1 index, so that's what we return. And in this last example here, we have a target of 7 with the same array. That should go at the very end, and so that would be 0, 1, 2, 3, 4, basically creating a new last index there. So a binary search is going to take big O of log n time, because every single time it basically cuts the array in half, so it's a very fast algorithm. Basically what we do here is we would get a index at the beginning, L is equal to 0, and if we had n is equal to 4, where that's the number of elements in the array, then that is going to set the r index at n minus 1, which is going to be 3. Okay, so we set up our two indices right here, and then we iteratively calculate a middle index, which is going to be L plus R over 2. That is going to give a value of 3 plus 0 over 2. Integer division, that'll be 1.5 rounded down to 1. So we'd get M is equal to this index right here. Now we would see that we want to basically search on the left of this because our middle value is too big. It's bigger than our target. So we would adjust R to be M minus 1. So we have L and R equaling each other. So we are searching for a target of 2. We may actually be able to find that target. So we want to run this while loop while L is less than or equal to R. Okay, we want them to run on the iteration they're equal to each other to see if we can find that value when they are the same index. Now it turns out we can't find that value here, and so they would actually end up crisscrossing because we'd get this as our m. They are going to crisscross here, and we will lose the constraint of while L is less than or equal to R. So what's going to happen is that m is actually going to be the last value that we looked at here, and that's all that we're considering here. So we ran our while loop here, so we're out of that now, and we're just looking at m. So we look at our middle value nums at m here, and it turns out that we have that is less than the target t, which is 2. So since it's less than it, that tells us that our target should have been located at m plus 1 here. Okay, it should have been located at 0 plus 1, which is 1, and basically that would force all of these to have shifted over here. So it should have been found like this, where we had 2 right here. So that's what we'd have if nums at m is less than the target. But let's suppose a different example where we actually were searching for the target of 4. Well, if we're searching for 4, well, we'll do the same thing again, L and R, and then we would get our m is L plus R over 2. M is going to be right here. Now this time we are comparing 3 to 4. So 3 is smaller than 4, so our target is bigger. We would end up searching over here, and so now m is going to be 2 plus 3 over 2, which is 2.5 rounded down to 2. So m is going to be right here. And from here we see that our target is smaller, so it's smaller than this middle value here. When it's smaller, that means we'd want to set R to be m minus 1. We'd want to look over here, but now they crisscross, and we have now this situation where we're looking at m, but nums at m is bigger than the target. Okay, so we compare this one more time. It turns out that nums at m is actually bigger than the target, and so we were on the right side of it. They are equal to each other. We get our middle index m, that is equal to L plus R integer division, so double slash over 2. And this is just traditional binary search here. If nums at m is less than
Hey everyone, welcome back, and let's write some more neat code today. So today let's look at LeetCode 35 search insert position. So we're given an array of distinct
Well, why is it fucking lagging? Fucking kidding me.
Just like this one down here.
You fucking
and the target value in this example, the target value is 5. And we want to know, does this 5 exist in this input array? If it does, if we found the target, then we return the index. In this case, the index was 2, right? 0, 1, 2. But there's going to be some cases where we do not find the value. In that case, we're going to return the index if we were to insert the value in order. Conveniently for us, the input is sorted. So in this example, 2. Now 2 is not in this array, but we know that in order it would go over here between the 1 and the 3. So in that case, we would have a output array or a new array of 1, 2, 3, 5, 6. Now the indices of this are going to be 0, 1, 2, 3, 4. So we're going to return 1 because that's the index that we inserted our 2 at, and that's what they tell us in the example. Now your first thought might be, well, since the input is sorted and we're given a target value,
yeah, just like sort the thing.
Then can't we just go left to right and just, search the array starting at index 1? Is this equal to 5? Nope. Is this equal to 5? Nope. Is this equal to 5? It is. So we return
log
value
of
2
n squared
because that's the index. So this is actually easier than you'd expect, right? This is the easiest solution. It's not even a bad solution. It's O of n. We didn't need any extra memory. This is a pretty good solution. But my question is, can we do even better than this? Is it even possible to do better than linear time O of n? Is that possible? Well, the hint that they gave us is that this input is sorted. Can we use that to our advantage? Can we maybe do better? Can we get a solution that's
fucking
log n?
bitch.
And the answer is yes. How are we going to do it? Well, there's a standard algorithm that's called binary search that you may have heard of. And I'm going to show you how to code that up to get the most optimal solution for this problem. Now, the reason we're doing binary search is we don't want to have to go through every single value and potentially check it. So we're going to do a slight shortcut. We're going to use the fact that this is sorted to our advantage. Now, binary search works like this. We get a left pointer and initialize it over here. So at index 0.
How should I go about this? I need to write a for loop, so L, comma R. I mean, binary search. And middle value is going to be length okay, while L is larger than equal to R, I need to search for if should I search with the left pointer? No. If the target is bigger than the middle index, smaller. Okay, bigger than middle index. So middle index is bigger. That means it's in the left side. So I need to change right side is equal to the middle index. And the new middle index would be is equal to divided by 2. Else, if it's in the left side, same thing. L is equal to M, and middle will be the same thing, right? And when we find this value, what we need to do is we need to what do we need to do? I think we need to we're never gonna find it sometimes. That's the whole premise, right? We will never find it. It's whatever, it's fine. It's not big of a deal.
We get our right pointer and initialize it over here, and that index is 3. And now we need to compute the middle. Because we don't want to have to start from the left and then check every value, and we don't want to have to start from the right. We're going to update our pointers and shift middle pointer, and we're still going to compute the middle the exact same way. So 0 plus 3 over 2 is going to be 1. So we don't have to update our left pointer. All we have to do is take our right pointer and then shift it towards the left. And since we don't have to check these values, I'm just going to cross them out because we know they're too big.
Get like a bigger example,
Then O event is our left and right pointer one, which is the rightmost value. So we're the right pointer, which makes sense, right? The middle pointer 2. In Python, you need to find our target. Did we get nums of middle index equal to the target? If it is, we know that we can return that middle index because that's middle. Or, and I'm going to explain, in an array with just 97%, that's why we want to do log n, because it's the most efficient. But why are we returning the left pointer? Let me explain. So what if we had a target of 1 and an array with just one value 2? Then we would have our left pointer here and we would have our right pointer here. But we would see that 1 is less than 2. So we're going to start searching to the left, meaning we're going to take our right boundary and put it over here. But clearly, now our pointers don't make sense, right? Left should not be to the right of right. So in this case, we're going to stop, our code is going to stop, right? Our loop is going to stop. We're going to return left just like we wrote in our code, and left is equal to 0, right? That's the index that it's at.
Bro, why?
And that's exactly what we want to do, because once we take this 1 and insert it, our
I think I've done like enough stack problems, monotonic stack. Have I done enough stack problems? Probably.
Hey guys, Greg here. What solves?
So this is the linear search doesn't really work. Just like you just have to like go through that and try to find the number and return it. And this is the, if nums is equal to mid, return mid. Return mid, yeah, the index. Okay, if nums is bigger, okay. Okay, he has like 3 cases. So at it's equal, you just like return mid. If it is not equal, same thing what I did. Why is it just 1? I don't get it. Result. Extra memory though. Yeah, I get it. Okay, result is equal to length of nums. Why? Why is it length of nums? I don't know. Binary search too. Like, why is there like 2 solutions for the same thing? I think this is what I did anyway. I don't need it. And fuck you. I gave her. Yeah, I think this is what I need. I need to like use the left pointer as my result. Return L. Calculator, nigga, who needs it? Yeah, obviously I need to do this thing right here. I need to start with it, I think. So if this is true, I just have to yeah, return mid, return M. If obviously you forget this sometime, but obviously yeah, we're not doing this. What are we not updating the mid? Oh, it gets automatically updated. Okay, cool. Till we find it. So when so what happens when we don't find it? Bro, I don't get it. Like, target is 5. I just return the index of where it's gonna be. Oh, it moves to the next thing and it like, huh. So let me like draw this out. Let me do like a bigger example for myself. So we have -1, 0, 2, 4. It's all sorted. Cool. And the left pointer is here, right pointer is here. And what we're doing is the middle. I mean, it's the same thing. It's a bit more cleaner when it like each like kind of gets reduced and added. Okay. So the middle will be 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6. 6 minus 1, 5. 5 divided by, I think it's this one. Whatever. Doesn't really matter. So it goes on the first loop and it like, that's the middle value, okay? If nums of middle, if 2 is equal to the target, what is the target in this particular example? The target is 10. Is 2 equal to the target? No. If else if, please. Else if the target is, if it is not bigger, so it goes onto this condition and it goes, okay, let's increment. We're incrementing the L and the middle value changes. And the middle value changes again. The middle value changes. On the last loop, the middle value is the right value. And what happens here? So what is L? L, oh, that's so fucking smart. L is just this plus 1. So this is going to be, R is going to be whatever. Let's say the 1, 2, 3, 4, 5. Let's say R is 5. L is going to be 6 at the end. And that's where it's belong. Enama. Varva.